We are now happy with the, I would expect, even though maybe you are not that happy, but I expect you are happy with the multicollinearity problem, right? So now you know what it is, right? So let's say I would ask this question. So if someone, let's say, like, if your child come approach you and ask, mother, what is this number about? How can you explain?
I just know that this is. At first, I need to define what it is. This is the conditional number. It's about is equal to the maximum of eigenvalue over the minimum of eigenvalue, and it represent for if the high if it has the high value, so it represent for the appearance of correlation between the variables.
Some variables.
Yeah, some variables. Yeah.
So that is another measure of the collinearity.
Yeah.
But let's say this one is not direct.
Yeah.
It just indicates that your matrix.
Indicates. Yeah.
Yeah. Is we have let's say some kind of ill behavior, but it doesn't tell you which variable
Yeah.
is the problem.
Yeah.
And if you have the VIF, you would know immediately.
Yeah. Yeah.
Get it?
Yeah.
Okay. That's pretty much what we have for the multicollinearity. For the normality, it's just like this one, right? The skewness. How can we go now? Let me ask you. How do we compute the skewness of the data? X minus mean to the power 3
Yeah.
divided by n. Right? So how can we compute the kurtosis?
4.
2 to the power 4. That's it. So you know how to do them all, right? Like the deviation from the mean squared up to the third or to the fourth power. So these are simply, if you compute them, you will be able to compare with the chi-square and see if the error term. So these are the tests to check or to diagnose if the error term follows the normal distribution. Fair enough?
Mm-hmm.
So I will not discuss the back and forth here, but for sure you have to be right. Okay, so I don't say anything about the exam. You to apply. Okay, let's move on. This is a problem that the error term, this is a fitted, this is the y hat, and this is the residual. And somehow you see that the residuals are quite concentrated around 0 when the values of the fitted values are small, but it becomes more spread as the fitted value becomes large. The fitted value is the combination of the axes. So there is evidence that when the axis becomes larger, the error term has a larger variance. So the error term is not IID, right? It's not IID. So in this case, IID stands for independently and identically distributed. This identical is no longer valid because it varies. Identical means it stays the same. Is that right? Clear enough? Fair enough? Good. So how can we represent that? Right? So let's say when we have the problem of so we have the model that in this case beta y is equal to x beta plus epsilon. Assumption number 4 is violated. So assumption number 4 is often known as the spherical assumption. Here means that the error terms are not correlated and they are homoscedastic, meaning that their variance stay the same regardless of the value of the explanatory variable. Let's say when this is violated, how can we say that? So let's say when it is violated, the variance covariance matrix can no longer be written in this form, right? But it has to be in this form. So basically, behind this formula, we are assuming that the variance covariance matrix of the error term is no longer of the form sigma squared times I anymore. And if it is not sigma squared times I, you cannot group you cannot simplify the variance covariance matrix. Right? So if this is the case, you would say that X transpose X to the minus 1, X transpose sigma square I X, X transpose X to the minus 1. The I here is gone because it is an identity. The sigma gets out, right? And you would see that X transpose X will cancel out each other. So you have sigma square X transpose X. So basically the idea is this one. If the data is follow this formula, but you, for some reason, use this formula, the standard error that you compute is no longer correct. Fair enough? So that's the message. So it has nothing to do with the estimate. Because the expectation of the estimated coefficient is still equal to the true value. So what you estimate is still valid, but the confidence interval is no longer valid. Agreed? Get it? Very clear, right? Chung? Not sure. Say it again. Right? Say it again. So let's say basically when you run this question, what do you want? Okay, I'll write it this way. I have to thank COVID. I mean, before COVID, I was using this software already, but it was not this handy, right? So let's say what you want. You would say with this model, if all of the assumptions of the OS are satisfied, you want to have beta hat equal to X transpose X to the minus 1 X transpose 1. Is that right? You will have variance of beta hat is equal to X transpose X to the minus 1 times sigma squared. You know this, right? So we know the value of beta hat. We know its variance covariance matrix. So we will be able to kind of draw the distribution of beta hat, any beta k, right? So we know, this is the beta k, right? And this is the confidence interval. You won't be able to define, so beta k is equal to beta hat k, given the data set, and the confidence interval is here. So if, by saying that we acknowledge this value could be, if you have the next sample, it could be somewhere here, it could be somewhere here. But we acknowledge the randomness in the data that we have. So by estimating this, you have this one, right? This purpose. The problem is, this one can only be written in this way if, this one is only true if expectation, let me just say expectation of epsilon transpose is equal to sigma squared times I. Okay? Good? If this is not, then this is, it is not, but you still use it. So you are using the wrong thing. If you are using the wrong thing, you will get the wrong answer. Okay? So if this is the case, if it's not the case, let's say if it is equal to, let's say omega, then you have to find a way to So let's say that in that case the variance of beta, in that is again the variance of beta hat will be equal to x transpose x to the minus 1 x transpose omega x transpose x to the minus 1. You have to use this one. Right? You have to, this is the correct one. So you, if this is the case, you cannot use this one. You have to use this one. Okay?
So the thing is, so we have to compute the variance beta hat first, and then if the expectation of equal to sigma squared, so then we have to change it to find the new variance of beta hat.
No. If we know that this is not the case, we don't do this. We do this. We have two choices, right? So let's say we assume that of the 6 assumptions, 5 are correct. 5 are satisfied. Only the 4th one is now either yes or no. If yes, do this. If no, do this. If no, you don't go this way anymore. Okay? How to do this? This is the topic of the next slide. Right? So let's say if Chi Chung is asking, so how can we proceed? And this is exactly what I'm going to do. Okay? So let's say, basically the idea I want to give you here is the variance of beta hat. The variance of beta hat given x is equal to this one. Right? So after some manipulation, I have it is equal to this one. And if there is no sigma difference. Okay? Good? Now, so I will actually in computation programs, people will not use the eigenvalue, the single value decomposition that I presented in the lecture. You know, we started with the eigenvalues, we have the eigenvectors, we have the Q matrix, and then we take the square root, let's say, in reality they don't take this part, right? They won't use the QR decomposition for the sake of being more efficient. So basically, the idea is this one. But I take the eigenvalue because the eigenvalue was later used in other circumstances. Right. This one. But basically, the idea is this one. If matrix A can be written as equal to, let's say, Q lambda Q transpose. Remember that? Okay. So if A, so the lambda matrix will be of this way. Lambda is equal to, this is lambda 1, 0, 0, 0, 0, lambda 2, 0, 0, dot, 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 0, 0, 0, dot, 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 lambda n. This is the matrix of the eigenvalues, right? And the eigenvector will be computed for each eigenvalue. You will have one eigenvector. If you put all of the eigenvectors into the Q and you normalize them, you will be able to rewrite to decompose A into this format. If A is positive, semi at least, that means that all of the lambda I will be larger than or equal to 0. If it is larger than or equal to 0, right, then you won't be able to write lambda 1 over 2, right, equal to, what is it?
Square root.
Lambda 1 square root.
Oh.
Is that correct? 0, 0, dot, 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 0, 0, lambda 2 square root, 0, 0, 0, 0, 0, lambda n square root. Okay? you will write A equal to Q times lambda to the power 1 over 2. Is that correct? Times lambda to the power 1 over 2 times Q transpose. Lambda to the power 1 over 2 or lambda, they are both symmetric matrix. Because if you transpose them, they are the same. Right? So, in this way, you will have the matrix lambda Q times lambda to the power 1 over 2, and then you have the matrix Q times lambda to the power 1 over 2 transpose. You call this one P, you call this one P transpose. Any square symmetric matrix that is positive semi, at least positive definite or positive semi-definite will be written, can be written in this way. So what do we mean by positive definite and positive semi-definite? You have a positive number. A positive number times 4 is positive. Times minus 4 is negative. Okay? A positive number 4 times 4 square is always positive. So if you have a matrix that is, if A is positive semi-definite, you will have X transpose A. X will be always larger than or equal to 0. If it is negative definite, positive definite, but not semi, then it will always be positive. So how can I know that a matrix is positive definite? You look at the eigenvalue. If all of the eigenvalues are at least 0 or higher, it is positive semi-definite. If it is all of them are positive, it is positive definite. If all of them are negative, it is negative definite. If all of them are either negative or 0, it is negative semi-definite. So if it is negative semi-definite, you won't be able to opposite. Let's say I might say opposite. If it's negative semi-definite, you will say X transpose AX. For any X, okay, any X, different from 0. Of course, if it is 0, it is trivial. You see, it always equals to 0. If the axes are all 0, right? All the elements in the axis are 0, it doesn't matter. But let's say if it's different from 0, it is positive. Good? Okay. Intuition. Of course, we have to look at more, trying to do that until when you become a professor. You remember how to do it. If you want to do, to have your head permanently. A PhD stands for permanent head damage. That's it. Okay. This is exactly what I need, right? So all of that discussion here is just to convince you that I can do this. Okay? Yeah. If I can do that one, and then I would define this one in this format, and then I would follow the rules, I can write it in this way. So if I take omega, I define the P matrix in this way, then you see that if I take P times omega times P transpose, it will be equal to identity. Just a preparation. I will use this result now. I will use this result here. Right? So now, let's say, if I take the P matrix I defined before here, right? Remember that? P matrix times Y, P matrix times X, P matrix times epsilon. I have Y star equal to X star epsilon beta hat plus, let's say this is beta, I'm sorry. Plus epsilon here. I want to erase it.
White
I
color.
want to erase it. How can I do that?
White color.
The white color.
cuộc sống à.
See, I don't do anything wrong anymore. But this is a bit tough. Yeah. So you see, this is I have by computing the P matrix, I have transposed the original regression model into something different.
Mm.
Now, so what is the consequence? I will have the expectation of P times epsilon given x is equal to P times epsilon, because P is a constant matrix. Expectation of x given epsilon given x by the assumption number 3, it is still 0. The variance of this one is equal to sigma squared times I, so it is homoplastic. Yeah. So this model we can use the OLS again.
Mm.
Get it? Get it? Mr. Jishu, you get it? Okay. So in Python, if you want to test, you have to do this.
You missed the omega matrix there, right?
Which one?
Just DE and then combine. Yeah, the one below before the like the variance of the new residual. There should be P omega P T.
It should be omega here,
Yeah.
right? And that should be an identity. Because that is grouped above here. Right? See? Okay. So let's say, in order to know if the assumption of homoplasticity is valid, we would follow the first one is we will follow the test hypothesis. First one, the H0 is that all of the sigmas are constant and equal to sigma squared. The alternative is that sigma squared depends on a function of the axis, and this one is known as the Bruce-Pagan, the so-called Pagan. What's that? The Bruce-Pagan test. Right? So if you run, so let's say basically now you run the OLS, you predict the sigma hat square, you regress the sigma hat square on this one. The null hypothesis is that the gamma 1, gamma 2, and all of them are 0.
Mm.
Okay? If they are 0, it is homoplastic. If they are not 0, it is heteroplastic. Okay, so this is what we know. Right. You seem to be lost. From where? From here? Yeah, from here? From here. So basically, assuming that now I have the matrix P. Okay, I will take the P. Pre-multiply the whole equation. Initially, I have it equal to, I have the equation y equal to x beta plus epsilon. Now I pre-multiply, I change the variables. And I change the error term. And if I change the variables, I will be able to show here, once the equation and the variables are transformed, they will satisfy the homoplastic. Right? So that is the way, right? So if it is heteroplastic, I have to find a way to do this. And then the question is, which way to take? Take the simple one, OLS, or take the heteroplasticity. You have to test. In order to test, firstly you run the OLS model, okay? Then you predict the error term, E hat. You square it, right? And you regress the square of the error term on gamma 0 and all of the explanatory variable. After running that, you will test for the relevance of x1, x2, x3, and xk. If these variables are not relevant, you conclude that the model is homoplastic. If at least one of the variables are significant, you say they are heteroplastic. And this is how we test it. we run the model, we take the R squared, you take R squared times M times R squared, you get the Lagrangian multiplier test. If this is correct, then this one will follow a chi-square with k degree of freedom. Fair enough? So now you know what the Lagrangian multiplier is. Is that right? That's why I spent time on the last time talking about the Lagrangian multiplier. Otherwise, we need the input just here. But let's say now I say this one is the Lagrangian multiplier. You know, at least if you have forgotten, you know which line to come back. And then if you know that, we can compute this one quickly. Okay, so you have to implement this in your own computer, right? Apply.
Is this really this line? The R square right here is the R square from the other right?
R square of this regression. The new R square. The R square from the auxiliary regression. Right?
So like you have to do the y regress on the x.
Yeah, you regress the
Yeah.
y on the x and get the
Residual.
residual, right? Let's say the step is that you regress y on x and get EFT. From EFT you do this one. Okay. So let's say I can be more precise here. Or let's say more clear here, so that you know that the R square here is the R square from the auxiliary regression. Good. Everything is clear. You know how to apply that into Python, right? Now, let's say in the examination, if I say all of the steps have to be computed manually, every time you use the written command, you would be subtract something. That's it, right? If I don't say that, you can only need to compute the last step and use all of the others in the written command, right?
We test for all of the coefficient except for the constant is equal to 0, so we use the LM. So we can also use the f-test, right? Because when you do the regression, the f-test will appear there. But the Lagrangian multiplier, you have to calculate another one. Because in the OS result, they give you the f-test.
Actually, they use this one because the LM test perform better than the world test in the large number. So if we want to compute this omega, how can we do it? So when we confirm that yes, there is a problem of heteroclasticity. Then we have to compute the omega matrix. This omega is computed in this way. This is omega. So basically, you regress y on x using OLS. You predicted the ETH square, then you compute this matrix. So it's a k by k matrix. So the outer part is the same, the outer part is the same. In the middle, you have the correction term. And this one is known as a sandwich covariance matrix. Right? Remember that one? So basically you have to do this. Now, I think I have prepared the code, but I think there will be not enough time to proceed. So again, it will be your job to spend the time on it, and I hope, I mean, surely you know that I don't write it manually, right? Because I'm old and I keep making mistakes all the time. But this is done by ChatGPT and I check it. If it is wrong, I will fix it. But let's say the code would be written by ChatGPT much faster than I can. Okay, so basically, the formula looks very daunting. To be honest, the formula looks very daunting. Is that why Mr. Chichu? Right? But when applying it to Python, it's superly simple. Right? So let's say, what do we do? This is so circle. So let's say in the basically you will do the regression. Let me show you. So in the Python written library, if you think that the residuals, or let's say the error terms, suffer from the problem of heteroscedasticity, if you type, let's say normally you would have none of the indication. Let's say now I want to put it down here. For comparison. So let's say if you do this, you are worried that the model is heteroscedastic, and you correct for it. So how do you correct for it?
Robust.
You correct for it by first regress. So let's say implicitly the software will do two things. Firstly, it will keep regressing y on x as usual, get the predicted error term, square them and put them here, and compute the new variance covariance matrix for you. Right? So basically it is in Python, if you want to do it automatically, very simple. Fair enough? So let's say if we do that, we can show. So this I deliberately included the code here, and just for you to see. Of course, in your report, you want to have a table like this, right? Agree with me, right? So your table must look like this one. This is how to do it. Just the code, right? You run all the models. So I already included the code here. So if you keep on knowing how can I have a beautiful publishable table, this is the code that we can do it. Okay? And it will give you the table like this one. If you have 10 models, it will give you 10 columns. Here we have 2 columns, right? And we start doing the eyeballing methodology to see if the variance, the standard errors are very much different. This one is 1177, 1188, 103, 104, 323, 299. This one, when corrected, is become even smaller. Then you have 97, 98, 8084. So there is not a lot of heterogeneity here, right? But you see that the standard error are more or less the same. So there is not a lot of changes. This is the, of course, we do not come to this class to do this. Is that right? We do not come to this class to do this. This is known years ago, not days ago, when you started with Michael Binder and those courses. So you know already. We come here to do this. This is how you are going to do this matrix. Okay? So, surprisingly, what I was kind of feel that it is so daunting was, how can I put this magic on? And I think ChatGPT helped me, and it could be done in a quite quick way. Right? So firstly, you take X transpose X. This is nothing secret. You have to take beta hat. No, right? This is what thing we would like, because you have to break it into steps. If I put everything into one line, you would feel crazy. But the residual is this one. Fair enough. The number 2 is, this is what I learned when I was preparing the lecture. If you have the list of the epsilon t square in one column, and if you want to create, because you assume no autocorrelation, so you want to put the epsilon t on the diagonal matrix, and off diagonal they will be 0. This is the command. This command will be nothing more than give you a matrix that of this form, of the form that is, here you have epsilon hat 1 square, 0, 0, 0, 0 epsilon at 2 square, 0, 0, 0, 0, 0, epsilon at n equal. So you have a vector column. This command helps you to create a new matrix. After having that, it just simply you take X transpose to minus 1. The matrix that you have X transpose times this matrix, right? By doing this, you have the component in the middle that is here. Okay? This here. And after that, you have the variance covariance matrix. Yes.
It's like there is different versions of variant. The HC heteroclasticity consistent variant. The one that you are using here is HC0. That is the one that happened after adjusted, like in the slide. In the slide is you have to use XC1, the Uber something, Uber Y version. You can show the slide and can say that would be the one that you show. Yeah, this is different from XC1. XC1 doesn't have this part.
Now this is H.
No, this is XC1. No, this is XC0.
You get what I'm talking about? This is now, I will turn it back. This is HC0. Now let's.
SC0.
Now when the HC0, it doesn't have the correction term here. For the one, it has the correction term. Right. So basically, the one is here. Okay? Exactly this one is here.
Yeah, it's
Let's see. I think that is not with me. Are you with me, that I explain once more. So, over the years, so let's say initially we don't have the n over n minus k here. This is the correction term. Yeah? So, if we specify the one that I wrote, the one that I have just shown you here, the one I have just shown you here, there is not the correction term of n over n minus k. Okay? There is not that term. Why? Because I am not correcting for it and it is known as HC0. Okay? If I put this one on, it is HC1. If I put this one, it must be HC1. Okay? Good? So let's say, let's say over here, we have the correction. I'm putting HC0. It is equivalent to doing this one. It is equivalent to doing this one. Okay? If I put HC1 here, it is equivalent to having the correction term over here. Yeah? Okay. This one is a complaint here. Right? So this is the 0, not the 1. The 1 is similar to the 0, but its formula is here. So it has a correction term, n over n minus k, to punish for the fact that if you include too many explanatory variables.
But
So, yes.
so for the second ones, the adjustment of epsilon t multiplied to n over n minus k. So if summation, so the
No.
n
This
we
one?
will square. I just I got it. I got that.
Mm-hmm.
I got that. But for the second SC1, if we approach that way for the SC1, The XC1 have the different adjustment.
Now let's say, I write down. So
Yeah.
maybe the easiest way is to say this one. So the HC0 is x transpose x to the minus 1, summation of t equal 1 to n epsilon hat square xt transpose to the minus xt transpose times this is what I meant, right? It is times x transpose x. So this is HT0.
Mm.
The same thing, it is n over n minus k, okay?
Mm.
And here is the number of observations.
Mm.
Actually, to be more consistent, I should have written n over n minus k. This is when I was reviewing the textbook. And sometimes I was typing from the textbook here and there. And they were using different notations.
Yeah.
And this one will be, the only difference is this term. Otherwise, it's the same.
Yeah, but when you plug in that into the summation, so summation of that equation become n times that, right?
Ah, you mean this one is n times n?
Yeah.
No, this is a row, which is k times k.
I mean that is because that's a constant, right?
Right, this one is a constant. No, which one?
So we sorry constant and multiply. So we take it out. No need to multiply with n. Not n time. Okay. I got it. I got it.
So basically, this is so the HC1 is a little bit. I call it the slightly different.
Yeah. Got it.
And people have come up with different solutions. Here, it's more complicated. Here is, they will use 1 over 1 minus ht. Where is ht come from? It comes from the projection matrix. The diagonal element of the projection matrix. So, what is the meaning of the diagonal of the projection matrix? So if the diagonal value of the projection matrix is very large, that observation is very influential. Right? If it is small, it's like the other ones, it is not very influential. And by this one, we are giving less, and we are giving more weight to the observations that are more influential. Okay. Now, and this one is another variant, just that, right? We talk about autocorrelation. Now, so if I don't say anything, you see, this is how we do it, right? So let's say in the examination, if the question is compute the h, I will give the math for sure. But the question is compute the correct variance covariance matrix of the regression model, and you know how to do it, right? So let's say, again, you have to spend time on looking at these weird functions that has become familiar to the computer guys. But for us, they are very foreign. I think we have now become an economist. So I've forgotten about what you did some years ago, but let's say this is the idea. So let's say I also included the case for HC2 when you have the 1 over HT, right? HT is the diagonal of the H matrix. So actually, I was not very, this is the diagonal. So this is the let's say I should have been more consistent here, so I put the P matrix. Why so? Because it's always the projection matrix. Is that right? Good. So if we have a matrix and we just want to get the diagonal elements, just do this. It's very simple, and then you have a vector. Good. So these are the steps. You see that if you look at this one, I am implementing the HC0, HC1, and the one. So nothing there. So that could be in the example. Now, similar to the case of heteroscedasticity, autocorrelation does not affect the unbiasedness of the least square estimates because the assumptions of extraordinarity still holds. Specifically, expectation of beta hat given x is beta. There is no problem. As long as the error terms are unrelated with the explanatory variable. However, the standard least square estimator, the standard least square variance covariance matrix estimator. I was variance covariance estimator is no longer efficient as the variance of this one is no longer sigma square times I. Okay, fair enough. Serial correlation may arise in cross-sectional contexts when observations belong to the same group may suffer the same shocks which are independent to the other groups. We won't do it in this case. We will start it. Serial correlation is always a problem in time series. We will treat a simple case, of course, in this course, but how further details with respect to the time series autocorrelation will be treated in the future courses. I mean, by maybe he will be. Binder already talked about it a lot of that. Hassel will talk a lot about that. So you have repeated things at least 3 times, right? So now you have learned by heart most of the things. Now, it is also worth noting that serial correlation also exists in the context of hierarchical and spatial data structure, which are briefly discussed in the end of this course. So I don't think that I will be able to talk about hierarchical modeling. So I intended to include, last year I included another project about land reform. But last year the focus was much more on the data processing. This year we spend more time on computing. So let's say in order to know if the serial correlation is a problem, we have the Darwin-Watson statistics. It is included here for you to compute, but it's not very much use. We have the test for that. Okay, so I illustrate the problem of the serial correlation of order 1 and some derivation. You will see the variance covariance matrix will look like this one. So it's obviously not sigma times I squared. Sigma squared times I, right? If this is the one, what should we do? It is, I put it omega t here. It's really not. So if we use OLS, we would assume that it is I. It has nothing to do with I, right? I times sigma squared. But this has nothing to do with I. So if that is the case, what should we do? Of course, we can transform the model again. And after that, we will come back with the transform variables. It will be OLS again. If this is the ordinary display. Let's say yeah, so let's say for the test, we also have the so-called, this is the new test for serial correlation. So you run the OLS model, you get the predicted value, you run the regression again, and test for the significance of this row, right? Row I. So it will be if this the again we will use the LR test again, LM test again, and basically what do we do, right? So first you regress number 1, y equal x beta plus epsilon, and you get epsilon at t. Okay. Number 2, you regress epsilon at t on x. Okay, and you get the epsilon at t. Okay, you regress epsilon at t on summation of I1 till p of rho I epsilon at t minus I. Okay, and you get the R square of the auxiliary. Okay, you get the R square. The L and n times R square of the auxiliary again. It will be, if you guys bear with, let's say b degree of t. Fair enough?
I thought like we just do two, the second one we do the residual on both x and
But this is to compute the LM test. The LM statistic. Right? So let's say you are not testing this one, you test this one. So first you regress epsilon hat on this one to get rid of this part. You take the residual from regressing this one on this one, you regress again on the rho I, on the epsilon t minus I. Get it?
why we have to care about the part here again. That is
Because
another-
yesterday you did not follow me. In the LM test yesterday I performed. I said the time, so I speak Vietnamese.
So basically, we have to like do regression on the two side. First on the x and on the on the timeline.
Of other timeline?
I mean on the period, like
Yeah, the lags.
yeah.
No, this is let's talk about the LM test in a very general way, right? So you have y equal to x1 beta 1 plus x2 beta 2 plus epsilon, and the hypothesis is r times beta 2 is equal to 0, right? In order to compute the LM test, now we have exactly the same. This is x1 beta 1, and this is x2 beta 2. And we want to test beta 2 here, on 0. So the first step is, you regress y on x1, you get the epsilon hat 1. And you regress epsilon hat 1 on x2.
Really?
Yes.
That is not what we did yesterday. Yesterday we do y on the whole thing.
R squared.
We have E1 and E normal. It had
So at that time you were sleeping. Now, then you have LM, now I'll show it later. N times R squared here. The second step. Now, when we do the R square, that if we test all of the,
I remember that yesterday we have the 5x, and then we want to know whether we want to have 3 more x. We have the formula for LM, but that time we do y on the 5x first, y on the 8x, and then we
No, y on the 5x, get the residual,
Oh, really? Okay, so
and the residual on the
maybe
3
I
axis.
don't understand that. Yeah, okay.
Now you can get it, right?
Yeah.
Everyone get the same? Yes? No, how to do that. So exactly we are following exactly the same one.
Exactly the same.
Okay, so maybe we miss each other at that point.
Yeah, it's okay. I'm just thinking about something else.
Good. So let's say basically here we have the model. Now, Now I know that you are losing me, but I will keep pushing up. We talk about heteroclasticity, we talk about autocorrelation, now we talk about both. Okay, both heteroclasticity and autocorrelation. If we have that problem, we have to use the so-called heteroclasticity and autocorrelation consistent estimator. And the formula is here. The formula is extended in this way, so it is okay. This is how we will implement it. In the built-in function, it's very simple. But in and actually, when it is applied to Python, it is also overwhelmingly simple. Overwhelmingly simple. So here, I use a different data set. Here you may notice I use okay. I will fix it a little bit. I use a new data set here. I use consumption, and I demonstrate how we can compute the HAC variance covariance matrix in this one, right? So this is what I already included. So I'll share with you the code. But let's say this is the half, and we compute the half in this one. It's quite simple. The S, you need some time to do the eyeballing methodology to really get into the S, right? But actually, how the S is computed, it is here. So if you compute the math and compute the code, you look the code at the code and you look at the math, and you do it 1,000,001 times, you will understand how to code in Python quite smoothly, right? I mean, in this case, what is the key to success? You look at the code again and again and again, and you get used to it. Because this piece of code here is nothing more than the math formula here, right? So let's say the approach that I'm taking is I give you the math, and you will eventually figure out the code. But if I give you the code without explaining the math, you would have no way to remember. Is that correct? If I don't explain the theory behind, I just give you the code, it will be inherently difficult because you have to learn by heart things that you have to know. And if you get to know that these kind of code are just to imitate the math, okay? And why do you have to imitate the math? Because the variance covariance matrix is not an identity matrix anymore. It has the forms, and you assume the forms, and then you will try to apply that into Python. Fair enough? Okay. So to some extent, when applying Python, if you understand the math, you go back to Python, you will see that you will realize that things are very simple. It's 3 more minutes. I move to the last. I move to the last topic. That is the problem of endogeneity. Right, so we did this one, right? We did this one, right? We did this one already. We did this one already. And so the number 3 is the data generating process of the explanatory value. So they could either be fixed or random. Get enough? So if we fix this one, in the afternoon, we are going to talk about optimization, and then we switch to data processing. So I would need 30 minutes to go through this one. Right? They are beautiful math that derived by the lady there. Right? So this is I borrow from a basic story. This is not my product. This is from and let's say basically I borrow from her. But let's say this is I find that this is a beautiful way. I think she stole something from Michael Wheeler and something from other authors. But then I realized it is a nice way to present the problem of endogeneity, so I follow it. So let's say I still have 65 seconds left. So that makes it, let's say 9 minutes. I will take it back in the afternoon. Right? So let's say now you have lunch. We come back at 1 sharp and talk about the endogeneity. Then I talk about optimization. And after that we move to data processing. Right? And then we are on track again. And I'm sorry, but you have covered a lot of materials so far. And I have intentionally included detailed derivations of most of the results. So if some of you who have forgotten part of that or some of that, please go through it. And if you don't understand, copy that one, throw it to ChatGPT, say, hey, how can that crazy lecturer give me this formula? And ChatGPT will say, how? And let's say, what I want you to do, the message that you have to take away is, programming when you do not know what to program, it is a no-go. Right? It's no-go. So in order to learn programming, we must know something to compute. So in this, in our program, we are econometricians. We start with econometrics. And when we know what we have to compute, we will be able to do it either way. Either by ourselves or by ChatGPT quickly. Right? So this is the message that I want to give. Of course, the easy part is gone. So the harder part is data computation. We will do more in the afternoon and the day and the whole day tomorrow. With that, I wish you a very good lunch. It is exactly 12. Enjoy your lunch and see you at 1 sharp. Hello, Mr. Ziming, are you with us?